So welcome you all on this YouTube channel. So this is a question which is being asked in ESE 2020 examination. Question is like, what is the value of a steady state error for first order system 1 by st plus 1 with unit ramp function, right? What is the value of a steady state error for the first order system 1 by st plus 1 with unit ramp function? So out of these four options, A, B, C, D, only one option is correct that we have to choose after solving this question. So how to approach this question? Let us see. So here first order system is given. So that means the transfer function control output CS to the reference input RS is given as 1 by st plus 1, right? That is given first order system. Now the reference input is given as unit ramp function. So here reference input RT is given as unit ramp function. That means it is TUT. So that means in Laplace domains it becomes RT become RS and it will become 1 by s square, right? So I can put this value of reference input here and I can calculate this control output CS. So CS, it will now become RS into 1 by st plus 1. RS is 1 by s square. So 1 by s square in bracket 1 by st plus 1, right? So now we can do the partial fraction of this. So just do the partial fraction. So let us do the partial fraction. A by s plus b by s square plus c by st plus 1. So now take LCM, that is s square st plus 1. Here it will become A, in bracket it will become S, and here it will become st plus 1. Here it will become plus B and it will become st plus 1 plus here it will become C into s square, cs square, like this. So just compare it with this s square st plus 1. So we can further simplify this. The coefficient of s square will become c plus at. Just see here, s square coefficient is c and from here s square coefficient is at, right? So c plus at will become coefficient of s square plus, now take coefficient of s, it will become a plus bt, right? From here it is as into 1, that is as, so a and from here BST, so coefficient of S become A plus BT, plus what is remaining? Constant term B is remaining, which is free from S, right? So here S square ST plus 1. So now you can further simplify this and equate the coefficient of S, right? So S square coefficient is 0, S coefficient is 0, and constant term B coefficient is, so this denominator on both sides get cancelled. B is equal to 1, right? Coefficient of S square is 0, so C plus AT becomes 0, and similarly coefficient of S is also 0 here. So we are just comparing the coefficient of S square and S to the power 0. So coefficient of S to the power 0, that is B, is 1 here. Coefficient of S square C plus AT is 0. Coefficient of A plus BT is equal to 0. So A plus BT is equal to 0. So here you can write A is equal to minus of B into T. So B is 1, so A is basically minus T, right? So from here you can calculate C, coefficient C. C is equal to minus of AT. A is minus T, so minus of minus T becomes T square. So C is T square, coefficient of B is 1, right? So we have now calculated A, B and C, right? This is the coefficient C, alright, and this is the coefficient A, alright. Now simply put these values into this partial fraction and just further solve. So here your CS, the control output in Laplace domain, it will become A by S. So A is minus T, so minus T by S, plus B by S square. B is 1, so 1 by S square, right? And plus C by ST plus 1. C is basically T square, so T square divided by ST plus 1. We can further simplify this, so you can write 1 by S square minus T by S, and from here, see, in the numerator it is T square, in the denominator it is ST plus 1. So in denominator take T as a common. So when you take T as a common in denominator, it will become S plus 1 by tau. So T in denominator get cancelled with T in numerator. So finally it will remain T by S by 1 plus 1 by tau, 1 by T, right? So that is the controlled output in Laplace domain. So now if you take the inverse Laplace, then you can get CT is equal to T ut minus T, capital T, ut, right, plus from here you will get capital T e to the power minus t by tau. So that you will get. So now the error signal, we have to find the corresponding error signal, right? So the corresponding error signal we can find out from here. So the corresponding error signal will be the error signal that you have to calculate will be ET is equal to the reference input signal RT in time domain minus the controlled output CT in time domain, RT minus CT, right? So now put the values. RT, you know, it is given as unit ramp input. Ramp input is given. It is given as unit ramp input. RT, reference input is given as unit ramp. So now RT is TUT, that is TUT minus CT is CT will be this whole term. Let me rewrite this term. So ET will become RT minus CT. RT is T into UT minus CT, control output CT is this one, TUT. TUT minus small tut minus capital TUT plus T e to the power minus t by tau. Put this whole value here. So small t ut minus capital T ut plus t e to the power minus t by t capital T, bracket closed, right? So now TUT and TUT get cancelled from here. Finally you are left with T in the bracket. It will become 1 minus e to the power minus t by t. So that is the error signal ET in time domain. So now you have to calculate the steady state error, because he is asking steady state error. So finally the steady state error, steady state error will be equal to limit t tends to infinity, that is ET, and ET is t 1 minus e to the power minus t by t capital T, right? So when you put a small t is equal to infinity, this exponential term becomes 0, because e to the power minus infinity becomes 0. So finally what is remaining? Finally t is remaining. So the steady state error will be equal to t. So t is the answer. So which option is correct? Option B is correct option. Option B is correct. Option B is correct. Steady state error is equal to T. So that's how you can approach this question. So thank you very much. For all such kind of exam oriented questions, please subscribe to this channel. Thank you very much. Thanks for watching.